Hi, here to talk about 10.8, which is the cosine and sine functions according to our book. Really, it's looking at graphing sine and cosine, kind of what you get when you do that. This first part here, with the unit circle, I'm going to use to kind of derive what the graph ends up being. I probably wouldn't frantically copy this down if I were you, but I would copy this graph over here on the right. And I'm going to start out just with the cosine function. And just want to review a little bit. If you don't know the unit circle, go check out my 10.4 notes. That talks about it a lot in better detail. The unit circle, we started with 0 degrees over here, worked our way around counterclockwise, so 90 is up at the top, 180, 270, and so on. And then the key to the unit circle is really this part here, that the x values on the unit circle are the cosines of the angle. So if you were to have some angle here, so maybe say that's like 41 degrees, that x value right there, which looks like it's going to be about 0.8, should be equal to cosine of 41, depending on how good I'm guesstimating my angle and such. The y value of that, which is going to be 0.987, 0.6, or maybe 0.58. So if you did sine of 41, you'd probably be somewhere around the 0.58, 0.57. Again, if I estimated my angle right. But okay, we're just going to do that for kind of the easier angles, the 90, 180, 270, 360, 0, so on. So if I'm doing my cosine first, my graph of cosine, I'll say, well, cosine of 0 degrees, well, my 0 degrees is this point over here. My cosine is the x value. So cosine of 0 degrees should be 1. I'm going to take and put a dot right there on my graph. Cosine of 0 degrees is 1. Now if I jump over here to 90 degrees, halfway to 180, what's my cosine of 90? Well, 90 puts me here on the unit circle. Cosine is my x value. So I'm going to be there at the 90. If I were to do the same thing for 180, so 180 brings me to the left part of the unit circle. Cosine is my x value. So I get a -1. It's right about there. Cosine of 270 gives me a 0. And cosine of 360, I'm all the way around my unit circle, back here at 0 again, so cosine will give me 1. Now if you look at this, it looks like a ginormous V. You could go through, if I grab my little straight line function thing, I could go through and put in a V. I wouldn't do this because this is wrong. And usually when I get on a quiz or test, somebody doing something like this, they get marked down. And the reason is, if you look, my x values, they don't change very much here. In my first 20, 30 degrees, I go from like 1 down to 0.9, then 0.8, I'm almost at 40 degrees by the time I get down to 0.8. So I can't have this drop at a consistent rate because my x values stay almost the same. Then towards the end, as you get closer to 90, they're really dropping fast. So what the curve ends up looking like, I found I do a lot better graphing if I kind of start at the top, work my way down, start at the bottom, work my way up. But get the dots like I did. Usually it ends up looking pretty ugly trying to do it here on my little wireless slate. Something like that. Ideally a little bit smoother of a curve, but you have it going almost horizontal, and then it starts dropping faster, faster, faster. Then I'm going to come over here to my 180 and try to do a similar thing. I'm at my 180, curving up. Wow, it's worse than normal. So I'm going to claim. But so something like this here. And so that right there is what the cosine function is going to look like, something along those lines. Just in all fairness or integrity, this is really what the curve should look like. Granted, the 180 should be right about in there and so on, so 180 degrees and 360 over there. But that's kind of the smooth curve that we're looking for if we're doing the cosine. Now the question comes up, well, what if you have more than 360 degrees? So say you're over here going over to 450 or 500 or back here in the negative degrees. Well, if you notice, we just started here on the unit circle, worked our way around once. Once we hit more than 360 degrees, we just start a second lap. So it's really just going to continue as well again, that we'd have this exact same start here, or this same start here on the graph, continuing over on this side. So if drawn correctly, it would keep going down here as well. And then if you were to go back and try to do this going negative, you'd have that same sort of curve going back the other way. So what it looks like, if you're doing multiple things, this here would go from negative 360 degrees. Over here we pass 0. We're back up to 360 again, right about there. Then another lap around the unit circle would bring us to double 360 or 720 degrees. So you'll notice that the cosine function just repeats over and over and over again as you continue doing laps around the unit circle. We could do the same thing for the sine function. The sine, though, is just going to be my y values. So we start over here at 0, go up to 1, back to 0, and so on as we work our way around the unit circle. So I'm going to quickly put that in. I'd add that to your graph or maybe make another graph. But now if we do sine of 0, because sine is the y values, sine of 0 degrees is 0. Moving up here to 90 degrees, sine of 90 degrees has to be 1. So over here at 90, then I'm up at the top at 1. And sine of 180 degrees is back to 0 again. My y value is at 0. Sine of 270 there on the bottom of the unit circle would be a negative 1. And sine of 360, back where we started, we're back at a y value of 0 again. And now then, if we take and draw this in, we get that same sort of a curve. I'm going to redo that one. So same sort of a curve. We're just kind of starting in a different spot. And again, I found that I have much better luck if I start at the bottom and try to do the curve up to the x-axis, and do the same thing starting at the top, do the curve down to the x-axis. I find that myself and other people that just start over here on the left to try to work their way around, usually you can hit the first point, you're kind of off crossing the x-axis here, and then you're really bad by the time you get down to the bottom again. But the sine should have that similar sort of curve. Or if I jump down here to what the graph really should look like is this right there. So that's really what it should look like. And just like with the cosine function, the sine function is going to keep just doing laps around the unit circle. So it's going to give us something like that. And again, we're going from down on this end, we're at negative 360 degrees. We pass 0, we have another 360 right here. And then over here at the end we're at 720 degrees. And I want to kind of back up and do two things. Well, first of all, if you're looking at the units on the x-axis, I can add in my 180 and add in my 360. But the units on the x-axis with the graphing program I used here, a program called Mathematica, really doesn't seem to fit at all. And if you try to figure out what's significant about this, it actually is a good hint for radian measure, which is chapter 10, section 10. And we're seeing this cross over here. We have 180, saying what's significant about that point there, or even here over at the 360. A little easier to see with 180. So why do we get that point for 180? Well, if this is 3 and this is 4, hash marks are a little bit tough to see, but that's broken up into 5 segments. So this black line right there is 3.2. So try to think of a significant number that's a little bit less than 3.2. If you think for a second, that hopefully gives you that 180 degrees right there on the x-axis. That's approximately the exact same spot, should be the exact same spot, if done right, as pi. So approximately equal to 3.14 should be equal to pi. That's going to be what radians are. We'll talk about those in a couple sections, but radians measure angles according to the length of their arc on the unit circle, and 180 degrees is the same as pi. But that's more coming up later. One other thing I wanted to mention, though, is graphing on your calculator. Because let's say we're trying to get this red one here, or a version of this red one, on our graphing calculator. So you grab your graphing calculator. Alright, and then we want to go in graphs. We start by pressing our y equals button. And then in there we want to do the sine. That's one we have on the screen here on the left. Sine of theta. So you hit your normal variable button, the x comma t comma theta comma n. You could end your parentheses if you want to, don't have to, because that's at the end of the line. But we want to graph this. And you'll notice that you probably don't get anything like your sine curve here. And it shouldn't be filling the whole screen because our maximum is 1 and our minimum is -1. But we should at least see something coming up here to 1 and a -1. And the issue is really in the settings on your calculator. That if you hit your mode button, you'll notice that you probably have your calculator set in degrees. Your graphing calculator is set to measure in angles in radians when graphing. So one option is to change it to radians, and you can do that. I probably wouldn't though at this point. Instead I want to show you one other thing. If you press your zoom button, you'll notice number 7 is Z trig. And if you press that, that sets up your calculator to nicely graph things that are normally going to be trigonometry. So sine, cosine, tangent. Most of those graphs are going to look pretty nice on your screen if you do that zoom trig. And that allows you to keep your calculator in degree mode. So as you go on and do other problems on a quiz or a test, doing like sine of 70 degrees, that is not doing sine of 70 radians on you. But also gives you something that looks decent on the curve. When you do that, your calculator is set to go from negative 360 almost degrees up to about 360 as well. Not sure why it kind of hacks it off there. Probably something to do with if you were to hit trace, that it's giving you a nice number of degrees now would be my guess. Allowing you to get certain angles like 30 degrees. You'll think back to section 3 and that's a significant number. So that's how I would graph it on a graphing calculator. Here I just have sine and cosine both put together for that negative 360 all the way up to positive 720 degrees. You'll see how they're cyclical, or we call it periodic, which brings us to the very last part of the notes, which is periodic functions. A period or a periodic function is going to be a function that keeps repeating itself over and over. And so if you have these two graphs, we're going to see these soon in the notes, they're periodic. So we have it going up and then kind of coming down, curving out, and then sharp up, coming down, curving out, going up, coming down, curving out. So it repeats the same thing over and over, so it's a periodic function. So a periodic function is going to be kind of my version of a definition, a graph, maybe I should say a function, that repeats regularly. And the period of that graph, or the period of the function, is going to be, I want to say the time, but really it's whatever's on your x-axis. If it's time, the x-axis, then it'd be time. If it's distance, then it'd be distance. But maybe we'll say value, or the values on the x-axis that it takes to repeat. That's a pretty bad definition, really. If you're thinking back to like my physics class, if you've taken that class already, then really we're looking at the wavelength. What's the distance before the graph repeats itself? So looking at a couple of these, so if we make this first graph bigger, I don't know if this is worth trying to copy down, but if you're trying to figure out the period, basically you find one part on the graph you can easily identify. I'm going to look at this bottom part here at 0, and you go until you get the exact same thing, and we have the exact same thing at 2, so the period would be 2. You could go through if you wanted to and do that same thing for a different part of the graph, like if you started there at the very top, dropped it straight down, went from there at the very top, dropped it straight down, you should get 2 as well. So you kind of want to look at where's the spot that you can easily identify, then go from there. You could, if you wanted to, also go from kind of the start of the curve here, missed it a little bit, but to the start of the curve here, so you could do similar things to something like that. I'm just trying to find shortest distance before it repeats. If I have this one here, one side we'd really like to see a little bit more of it to make sure it's periodic, but if you wanted to assume that that's going to keep repeating over and over, find a spot on the graph that you can easily identify, and right here I have this line here, which is kind of there at the maximum, and you go until it repeats again. So aim for right up there at the top. Looks like I missed it again by a little bit, but the period should be 11 on this, that it repeats at 11. If you would have picked a different spot, say we went from this one here, the mistake that I see people make is they go from like here to, alright, I'm going to go to this one right there, and it's the exact same height. But if you look, it hasn't totally repeated yet, because we'd have to have, just coming down off this very large one, then up to this. We have the two little smaller ones up to that. That this thing here doesn't really repeat until you've had another one of those large cycles in there. So you could go something like this, from the blue dashed line to the blue dashed line, just like we did from the red to the red, but here I'd have 13.5 minus 2.5, I'd get my 11 again for the period. This one here, there are some similarities like this here. Kind of looks like mirror images of each other, but it's not periodic. It's not something that repeats over and over. That is all I have for the notes on Chapter 10, Section 8.